Okay guys, so this is the, call out the camera, this is the higher velocity acceleration stuff, and there's a lot less of it, but there's an exam pro as well to follow, probably either next term. This is for you to review really slowly. So many of you started this question. This is question 1 on the higher acceleration video. Here's Amina's speed time graph from the start of the race. So Amina and Ben are going on a cycle race. So friends out, whereas they should be isolating maybe, I don't know. There you go, so that's that. And as you can see, I cut it off there because I got it wrong a few times, then began to reevaluate my thinking. Now the distance for the race was 400 metres. They should have been running around this 400 metre track rather than cycling, but there you go. Ben cycled the 400 metres in 64 seconds. This is Amina's graph, and Ben did it in 64 seconds. Now the punchline is, who won the race? Okay, show you working, 4 marks. Well, Ben did it in 64 seconds, the 400 metres. It looks like Amina finished in 80 seconds, but we don't know. I know that if we work out her area covered in 64 seconds, we'll see what distance she did compared to Ben. Now we know Ben did it in 64 seconds. Now how far, or rather at what time did Amina finish her 400 metres? So let's just take a look. What did she achieve in 64 seconds? So I cut off the graph at 64 seconds and I did some calculations for area. I broke it up into a triangle, a rectangle, and probably a little trapezium there. Yes, I did. It's very hard to see on the video, I'm sure. I went, rectangle, triangle. We don't, that's a little trapezium essentially. So if I work out the area under Amina's graph, then I will know whether she went further in 64 seconds or whether she did less distance in 64 seconds, and the one who does the greater distance in 64 seconds had to have been the winner. I'm guessing there's other ways of doing it, but that's how my brain saw it. So in 64 seconds Amina did she did this area here, half base times the height, half times 20 times 8, and this little middle chunk here is going to be 30 times 8 and this little chunk here is going to be half AB H. So my A is 8, my B is 5. Imagine that's a trapezium standing up on its end, and the height of it from 50 to 64 is 14. So the last part will be half. 8 plus 5 times 14. That's 80. That bit's 240. That comes to exactly 91, which means that Amina did her cycle in 64 seconds. She did 411 meters. In 64 seconds, Ben did 400 meters. Now, since she went further in the same time, she must have finished that finishing point, that finishing line first. Therefore, Amina won the race. I'll let you pause for reflection. Of course, you pause the video. I'm going to carry on to question 2. This next bit requires teaching, I'm sure. Let's get my originals out of the way. Now, I'll put it all on one page. This is teaching now. It's not just it's not just me going over something you've done easily. It's something you've never done before. Here is a velocity time graph of a car for 50 seconds. Okay, 50-second dash, and I reach a maximum velocity of 30 meters per second. Clearly the car's accelerating here, then decelerates a little bit, and then goes at a constant velocity. That looks quite straight. Either way, we're accelerating and we're still getting faster and faster, but at a constant rate there. So that's the story, and we did it all in 50 seconds. And the question actually asks, work out the average acceleration during the 50 seconds. Well, on average, no matter how curvy the graph is, I did 30 meters per second over a period of 50 seconds. So the average acceleration is the change in velocity over time, which is 30 over 50, 0.6 meters per second squared. And there's a couple of marks right there. Next one. Estimate the time during the 50 seconds when the instantaneous acceleration equals the average acceleration. You must show you absolutely must show working on the graph. At what point is my average acceleration exactly matching a certain point in time where I'm doing the average acceleration? In other words, I'm looking for a point in time on that journey where my graph would go completely parallel to the average acceleration line. So here's my average acceleration line going from 0 to 50 seconds worth of time over 30, a speed of 30 meters per second. So what you do, you grab your ruler and you put it up against the graph and you swivel your ruler until the line that you're about to draw looks as parallel as it possibly can to the average acceleration line. Is that alright? So you put your ruler against there, it seems to touch 12 seconds. That means at 12 seconds, in that particular instance, my acceleration at that instance in time of 12 seconds exactly matches my average acceleration for that entire little sprint in my car, whatever it was. Is that okay? So instantaneous acceleration is about the acceleration at a given point on the journey, but it seems to match quite accurately the average acceleration because that gradient matches that gradient at that point and not anywhere else. So the answer is 12 seconds. 2 marks. Question 3, dead easy. Distance around the track is 400 meters, blah blah blah, prove it. Okay, in 110 seconds I've got 3 little blocks of area, which is 3 little blocks of distance, or better still, just use the trapezium by itself. There's your A, there's your B, and there's your H. So originally when I did this sheet, I did that triangle, that rectangle, that triangle. It came to 400 meters. Well, if I want to use a trapezium, it's only 2 marks. So I'm guessing they want you to use a trapezium. Half A, well that's 50 from 20 to 70, plus 110, which is like the B, and you multiply it by the height of 5 meters per second. Is that alright? That still comes to 400 anyway. This is the higher level stuff, the higher grade. Now this is Sanjay going on the same track. This is his graph, his profile. Does Sanjay cycle the first 400 meters in a quicker time than Robin? You've got to show you're working. Well, this is the easy part. I know that for these 60 seconds, he covered a distance, he was going at a speed of, let's have a look, 6 meters per second. Is that all right? Yeah, on average. So let's just take a look. In the first 60 seconds, the distance he traveled is 6 times 60, the area of the triangle, half of it. So half base times height. So that represents 180 meters worth of journey. So if he's doing a 400 meter track once round, I've got 220 meters left, which is in this constant speed area, which makes life really easy because here I know that something times 6 equals 220. Is that alright? So if I take my time, which is going to be distance over speed, if I divide my 220, yeah, the remaining distance that's represented by a region here, if I divide that by my speed, I've got 36.7 seconds. So he's done 60 seconds so far, plus an extra 36.7 seconds in this region here. That comes to 97 seconds. Now, does Sanjay cycle the first 400 meters in a quicker time than Robin? Yes, he does. Because if we go back to the original question, we'll see that Robin actually did that track in 110 seconds. So Sanjay was a lot quicker. So Sanjay is approximately 97 seconds. So this is me doing a picture of how I was thinking. That 180 is easy. That 220 is the extra distance. So that plus that is 400. I know that the area is 220 meters. The height is 6. So what divided by 6? 220 divided by 6 gives me what extra time? Answer, 36.7 seconds. If you add it onto the 60, there's your 36.7. Altogether, 96.7 seconds. And I called it 97. Either way, it's quicker than 110. Okay? Question 4 is probably overkill. The graph shows the speed of a snowboarder for 2 minutes. Okay? So there's a 2 minute, coming down the slope, going real quick. What is the distance? There's 4 marks. Now, I've probably overdone it. The distance is done by, calculated by the area under the graph. I broke it up into a little triangle, a little trapezium, another trapezium, another skinny trapezium, another skinny trapezium, and a teeny little triangle. I mean, really, we could have changed this into just one big triangle, and this into a trapezium, that into a trapezium, that into a triangle. I think I've overdone it here. Either way, you've got to work out the area of each little part, then add up all the bits. So I'll talk you through it a little bit anyway. First part, I've called this area 1. Half base times height, half times 30 times 2 is 30. I'll go over just this one, but no more, because just a trapezium will be highly repetitive, so I'm not going to do that. So I've got a height of 2, and my second height before it goes on to the next trapezium, that height there is about 6.8. It's just one square below the 7th at 6.8. So it's half times the base of 30, and then that will be my A and my B, yeah? My A there and my B there. So if you like, it's a trapezium on its side. There's your A, there's your B, and there's your H. So I did that for every section and added up all the distances and came to 552. Again, there's a lot of allowance for that because some people may not want to break it up into quite so many pieces. I mean, I would recommend you just pretend this is just one big triangle here. Just go 1, 2, 3, 4 blocks. Either way, you'll get an answer around about 500, yeah? Work out the gradient of the graph at 70 seconds. So go along to 70 seconds, which is here. Go to the top, hit the graph, put a little cross there. Then you pick up your ruler and you swivel it like so until it's completely just touching at that one point, and draw it in quick. Now, to get the gradient of a straight line, you should make yourself a nice big triangle down here, but I just couldn't bear sort of drawing triangles amongst all my other little trapezia. So I did it on the outside. I went from here up to here, and I went from there across to there. The numbers aren't beautiful. I went as far as 0.8 up to 10, 1.8 up to 10, which gives me a wide difference of 8.2. But this one's quite easy. It goes from 0 to 90, so the x difference in x is 90 anyway. So that part's easy to see, 90. That part's more difficult to see, and all because I didn't want to start crash into this. Either way, difference in y 8.2, difference in x 90. My version is going to be 8.2 over 90, and that came to 0.091, roughly 0.1 meters per second squared. 3 marks. You can get your marks for showing the gradients on the curve, doing yourself a little triangle, dividing and specifying. Actually, no, there's no mark for specifying the unit because they give you the units there anyway. And that's all there is on the higher sheet. Okay, I'm going to sign this off for now and consider these 2 sheets to have been done. When we meet again, we may do an exam pro, or I might upload an exam pro anyway as a separate homework stroke classwork, as if you're in front of me, and I'll send you feedback in due course. Thank you. So how do we stop this thing now?